Historically, regular expressions are one of computer science's shining examples of how using good theory leads to good programs. Today, regular expressions have also become a shining example of how ignoring good theory leads to bad programs. That's from Russ Cox, the man with the most concise and elegant LinkedIn page I've ever seen. And if you're wondering if he's any good at Go, don't worry, he's done the LinkedIn certification, plus he's got a recommendation, so you know this guy's legit. 2 videos ago we looked at the good theory, and in this video we're going to look at the bad programs, and we're going to explore why almost every regular expression engine used today uses the least efficient algorithm. At the end we'll also spend some time with a recent stand-up maths video on regexes and explore some of the finer details about how that plays out, which should be pretty fun. Let's get started. Let's consider 2 approaches to matching a string with a regex. Both involve translating that regex into a finite automaton, and the finite automata look exactly the same. The difference is in the algorithm we use. The algorithm we've used in the last few videos was, I believe, first described by Ken Thompson, and so is often known as the Thompson algorithm, but I'm going to call it the lockstep algorithm just so you definitely know what I'm talking about. We'll review that one first, and while you're watching, I want you to pay attention to how much work we're doing. We'll take a pretty crude measure of work to be the number of edges followed, and we'll call each one of those a tick. With the lockstep algorithm, we start by resolving all of the states that are accessible only from epsilon transitions. These are then all activated at once. We follow 4 edges, and so this takes 4 ticks. Then we take our first character, let's say it's A, and we go through each active state following the transition for anything that matches an A character. In this case, that's either the A edges or the any edges, and any state with no valid transitions dies at this point. Then we follow all the epsilon transitions to activate all of the subsequent states. After consuming that character, we have 7 states active, and so the process took 10 ticks. If we follow this process again for the second and third characters, we get a match, and this whole matching process took 19 ticks. Now this algorithm seemingly involves checking all possibilities at every point, so we might think that instead it would be convenient to only check one possibility at a time. We might reason that in the worst case we're just going to do the same thing, check every possibility, but in the best case we might get lucky and get the right result before we check all possible paths. Let's try it out. We start at S and then check the upper path first. We then proceed through the whole graph in only 5 ticks. Very nice. Let's look at the worst case though, where our string fails to match right at the end. In this case we try the top path just like before, which takes 4 ticks. But then we have nowhere to go, so we backtrack, unrolling each of the transitions we made until we have another option we can try. In this case we try the edge 4 to 6 instead of 4 to 5. Ignoring the backtracking, this takes a further 2 ticks. Once more we have nowhere to go, so we try a different path, taking a further 2 ticks. And of course once again we have nowhere to go. This is a total of 8 ticks so far. We backtrack again, and since we've tried all the paths leading from state 4, we have to backtrack again all the way to state S. We then take the second path from S via state 2 to state 4. This takes 2 ticks. We might be hoping that since we've already tried all of these paths, we can just mark them as failed and not try them again. But recall that in the top path we actually consumed a character at this point, the character A, in the transition from S to 1. But on this path we haven't consumed any characters. So with this way of using the graph, we can't be certain that a path we tried before is going to be invalid if we got there via a different route. So we have to retry all of these paths again, only to see them all fail. Trying all those paths again took 6 ticks, so in total so far we've spent 16 ticks. And we're still not done. We have to backtrack all the way to state S again and then retry the third edge from S to 3. And let's assume that our algorithm isn't yet smart enough to know that it's impossible to match, given we've already tried the top path, which consumes the same number of characters. This takes us a further 8 ticks. That brings us to a total of 24 ticks for the backtracking algorithm. The lockstep algorithm, on the other hand, takes 18 ticks, 1 less than a successful match. If you want to verify that for yourself, you can rewind the video to check it out. Let's see if we can quantify the number of ticks that each algorithm is going to take, given some variations on this graph. With backtracking, each block has 3 paths from its start to its end, and each of these takes 2 ticks to follow. When we add a second block, it will also take 6 ticks to explore fully, but this is multiplied by the number of paths in the first block. If we add a third block, the logic is the same but multiplied up, making a total of 78 ticks. Add a fourth block and we've got 240, a fifth gets us 726, a sixth gets us 2,184. After 10 blocks, we've got 177,144 ticks. In big O notation, which is for another video, we would say that this is exponential time complexity. And when it comes to regexes, this is often called exponential backtracking or even catastrophic backtracking. For the lockstep algorithm, one block takes 6 ticks, 2 blocks takes 18, 3 blocks takes 36, the 4 here takes 60, and after 10, we'll still only be taking 330 ticks. In big O notation, we would call this quadratic time complexity, increasing with the square of the number of blocks we have and the corresponding input. I'll leave deriving the formula above as an exercise for the viewer. If you find it puzzling that two algorithms, both of which seem to be based on the idea of exhaustively checking all possible paths, would perform so differently in the worst case, I also felt this way. I read and derived a number of ways to explain it to myself, but I'll share with you the one that I found most compelling. Let's imagine that we're using the backtracking algorithm, but we decide to try performing all of the paths at once to see if we can find any efficiencies in that process. We start at state S and follow the first 3 edges, assuming they match, and then the second 3 edges after that, ending up at state 4. At this point we have 3 paths, the top, the middle and the bottom paths, but they're all currently active in state 4, so state 4 is active 3 times over. If we then wanted to diverge each path to states 5, 6 and 7, we would end up with each of our 3 paths branching 3 times, making 9 total paths active. But perhaps we can avoid this by deduplicating the paths and saying, okay, so state 4 is active, forget how we got there, forget how many paths activated, let's just consider that as one position and branch only 3 times. If we could do that, at each convergence point, that states 4, 8 and C, we can deduplicate and control this explosion of paths. But there's a problem. While the top and bottom paths here have both consumed the same number of characters, just 1, the middle path has consumed 0 characters. That means we can't treat all activations of state 4 as the same, because they might be at different points in the string and so match different things later on in the graph. Consider, for example, the string AB. If we took the middle path and consumed no characters, then we should be able to branch to all 3 edges. But if we took the top path, then we should only be able to take the bottom 2 edges, not the top edge, which requires us to match an A at a position where we've got a B. So we can't just simplistically follow all the paths at once and deduplicate, because each path might consume different amounts of the string and so have different consequences later. Now we could instead try deduplicating based on the active state and its position in the string, which is helpful, but it doesn't solve the exponential backtracking problem, it just removes some multipliers on it. So we're going to need to be smarter. Instead of taking every branch, we can think about it slightly differently. Once again, we take the idea of performing every backtracking path at once, but instead of just following every branch from our start state, we explore every path until it wants to consume a character, and then stop just before doing that. We take all of the states activated in that process as currently active. What we've done here is activated every possible backtracking path up until the point it consumes a character. This is equivalent to resolving all of the epsilon transitions, also called the epsilon closure. After this, we ask every path to consume a single character or die trying. And then we once again follow all branches which don't require us to consume any more characters and consider all states activated in that process to be active too. And once again, this is equivalent to the epsilon closure. We've now activated every possible path that can consume one character of the input. In this process, we've activated some states multiple times. For example, state 4 is currently active twice because states 1 and 3 both branched into it. State 8 is actually active 4 times, from state 5, state 7, and also state 6, which arrived via state 4, which itself had 2 paths going into it. Another way to think about this is that of all the possible paths through the graph that consume exactly one character, state 8 is active in 4 of them. However, unlike our previous attempt, since every branch here has consumed the same number of characters, we can consider every branch which arrives at each of these states as equivalent. It doesn't matter that state 8 has been activated by 4 different paths, because for the purpose of matching the rest of the string, those paths are all identical. So, considering all paths but only consuming one character at a time allows us to deduplicate the paths and control the explosion. This is in fact identical to the lockstep algorithm. There are other ways of proving this to yourself too. Another one I sort of like is that Given a set of active states, consuming a single character is going to, at most, activate every single edge in the graph. This means that the maximum cost in ticks for consuming a single character is the number of edges in the graph. In that case, then the maximum cost for consuming a whole string is the number of characters in the string multiplied by the number of edges in the graph, which itself is related to the length and complexity of the regex. So if you're scaling up both, as we've been doing here, the time complexity is quadratic, n squared, assuming that n is representative of both the number of blocks and the length of the input. However, if you're keeping the regex the same and only scaling up the length of the string, the time complexity is linear, which is pretty nice, especially compared to the backtracking algorithm, whose worst case is exponential even if you only scale up the length of the string. It's elegant, it's efficient, it's beautiful, and of course that's why every... Wait, what's this? What's this speck of dust on my screen? This has been here the whole video. Let me figure out what's going on here. Oh. Oh no. Oh no. These are two high-profile instances of something called ReDOS, or regex denial of service. One at Stack Exchange in 2016 and one at Cloudflare in 2019. Regex denial of service goes something like this. At some point, a programmer writes a regex which is vulnerable to catastrophic backtracking and runs it in an engine which uses that algorithm. Then, somehow, either accidentally or deliberately, someone provides some input to that regex which provokes the worst case exponential time complexity, or at least a pretty bad case, and this overloads the processing resources available to the system. This sort of scenario, of course combined with some other failures, led to these outages at Cloudflare and Stack Exchange. Of course, there have been others and other companies, I'm sure, and it's not very surprising. You can imagine as an engineer trying to persuade other engineers in your team that the regex engine built into your programming language just isn't good enough and we should really add another dependency to fix it. Of course, that's highly likely to be met with some skepticism, and so you use the one built into the language. And at some point, somebody's going to put the wrong regex in the wrong place and the wrong input is going to get to it. So why do the majority of regex implementations use backtracking rather than lockstep? Well, I'm not 100% sure, but I'm going to tell you a story which makes sense given the research I've done. For that, I'm going to need to recap a little bit of the history and also introduce you to some new regex features. As we've mentioned before, Ken Thompson introduced regexes to the world of software in the late 60s through a text editor he was writing or porting called QED. He used the lockstep algorithm, and in fact he used a pretty interesting version of just-in-time compilation that allowed him to compile regexes to machine code kind of live in process. Later, when he was working on the first Unix operating system, he also implemented a text editor called ed and implemented regular expressions there too. However, when writing ed, he didn't use the same lockstep algorithm he'd used with QED. Instead, he used the backtracking algorithm, which is actually why I'm slightly uneasy calling the lockstep algorithm the Thompson algorithm, as it's commonly called, because they were kind of both his algorithms. So why did Ken Thompson do this when he had a more efficient algorithm available? I think nobody really knows the answer to this, but the regexes that he was implementing with ed were quite a bit simpler. The machine that he was building Unix for was quite a lot smaller in terms of memory, and so perhaps there was a kind of a convenient reason to try and trim some of the fat out of the regular expression part of the editor. And in any case, catastrophic backtracking is probably not a huge deal in an interactive text editor anyway, because, well, the worst case is the user can quit the program and then start again. Probably not great in a text editor, but it's manageable. And it's a rare occurrence anyway. However, one day somebody suggested to Ken Thompson that it would be useful if you had a version of the searching functionality in ed, which of course uses regexes, to be able to search through a number of files on a whole file system. And Thompson realized he basically already had all the code for this anyway, so extracted it out of ed, produced this new tool grep, which is based on an internal tool he had, which I think was called S, and the legend goes, the very next day he presented it to his colleague, fully complete. And so the myth is that Ken Thompson wrote grep just in a single evening, which is a cool story and probably mostly true. But there is a slight issue with the technical decision making here. You've gone from an interactive program to a program which is then going to be integrated into other tools, which is a slightly different engineering problem to solve. So regular expressions started to worm their way in to various utilities throughout Unix, one of the most influential operating systems ever made. And maybe the algorithm chosen wasn't ideal for that purpose, but there will be plenty of time to fix that. One of the other neat features in ed was the ability to do find and replace with this sort of s/regex/replacement thing. And you could also use the ampersand symbol in the replacement to stand in for the match. So if you wanted to search for the string regex and wrap it in square brackets, you could just search for regex and then put bracket ampersand bracket to produce that effect. This is a very useful feature, but it would be pretty handy if you could do this with little parts of the match instead of the whole match. Then you could use it to swap words around and do all kinds of other cool stuff. This feature, which made its way into Unix version 6, released in 1975, is now commonly known as capturing groups. Let's see how we can implement them. Let's take this new regex. Its goal is to match a sequence of any characters followed by a sequence of one or more Bs. We're using capturing groups here to extract the two substrings. Since in this series we've so far been mostly focused on matching whole strings, I've also put in the caret and dollar symbols to clarify that we're matching the whole string, though for simplicity I've not reflected this in our graph. To implement capturing groups in backtracking is fairly intuitive. You just need to label certain edges as recording and note down your current position when you pass through them. If you end up backtracking and going back over a recording edge, then that's fine, you just end up rewriting the position. While we're here, and to prepare us for the final section of the video, I'm going to show you another feature of modern regexes. You will note that this regex has a problem. It isn't quite matching how we intended. In our minds, we probably imagined breaking the string into two chunks. The first one being everything up until the final sequence of Bs, and then that final sequence of Bs. However, the regex plus meta character is what's known as greedy. It wants to consume as many characters as it's allowed to, and then move on only when it can't consume any more. This isn't quite what we wanted. There's a regex feature that can help us here called non-greedy modifiers, and it's notated by putting a question mark after the plus symbol to change its behavior. The result should be that the plus modifier will now consume as few characters as it can before moving on. In a backtracking algorithm, we can implement this by changing the priority of the rules. Instead of following the loop back from state 2 to 1 first, we'll follow it last. And out of this, we get the behavior we want. With the lockstep algorithm, it's less obvious what to do with all this. If we take the same approach as the backtracking algorithm, the different possibilities all end up clashing, and we end up getting incorrect capturing groups. Even worse, it's not at all clear how we can implement the non-greedy question mark modifier if we're just going to follow every transition possible at every possible point. Take a moment to think about how you would go about solving these problems. Are they even solvable at all while retaining the performance benefits of the lockstep algorithm? How sure are you, and how much effort would you be willing to bet on it in a real-world situation? It turns out that both of these problems are actually solvable, mostly by tracking other bits of information along with the state and then treating that as a key to deduplicate on. Russ Cox has a great article on this, which I'll link on the ODE's website, and I think the original idea for the solution came from somebody called Rob Pike. But I'm not going to go into all that in depth now. Instead, let's check back in with Unix. The team implemented capturing groups in ed and the new tool sed, which you may have heard of. They did all this with the backtracking algorithm because, of course, that's what they had to build on. So, to recap, we have a backtracking-based regex algorithm embedded increasingly deeply in the critical early Unix operating system. But everything's still fine because regexes can still only recognize regular languages, and so they can, in theory, still pivot to the lockstep algorithm later. This is where it all goes wrong. I don't quite know how it happened, but here's a guess. Shortly after Unix 6th edition is released, Ken Thompson, the person who knows most about the theory underlying regexes, he's understandably a bit in need of a break or a change after years of Unix development, so he goes on a sabbatical to Berkeley. In the meantime, someone at Bell Labs looks at the regexes in ed and sed and such and thinks, well, these capturing groups are a pretty good idea, but it sort of bugs me that you can only use them in the replacement. It would be nice, convenient, consistent even, if you could use them in the search expression also. This feature, which is now called Backreferences, would then allow us to do some cool things. For example, take this regex, which allows us to match on repeated chunks within a larger string. Let's go through it. The first dot star matches any number of characters. The capturing group matches on any character one or more times, and this \1 matches whatever the first capture group has in it. That's the back reference. We finish then with another dot star to match the remainder of the string. This back reference is different from just repeating the dot plus section. It doesn't just match things that follow the same pattern, it matches exactly what was matched in that group. So this will match the and not match run the. So how do we implement this? A backtracking implementation is quite straightforward. You just add a special kind of rule which matches on whatever the relevant capturing group contains. When you reach it, you can check whatever is in the capturing group and then consume that from the input. But this approach won't work for lockstep. Let's imagine that somehow we manage to solve the capturing group problem in an efficient way. When we reach a point where we need to check if a back reference should match or not, we have a problem. Let's pick a point in the middle of the regex. At this point, we need to know which chunk of the 6 characters so far have fallen into the capture group and which hasn't, so we can match on the group that's been captured and not on the group which hasn't. But we could split this in 5 different places, and that's now 5 different possibilities we need to check. That's already not looking good, but when we move ahead by 1 character, we then have to follow the same logic again, but now with 6 possible places that it could split. The next time around with 7, and then 8, and so on. So the total number of branches this back reference is going to force us to consider is the length of the string multiplied by the length of the string. We can cut that down a little, but it's definitely not going to run in linear time over its input anymore. So we've already lost our efficiency guarantees. But believe it or not, this isn't even the worst of it. Remember that the whole point of lockstep is to process 1 character at a time so that we can treat all active states as equivalent. Well, we can no longer do that because for each of these possibilities, the back reference rule is going to consume a different number of characters. So very quickly, the lockstep algorithm falls apart. There's also a theoretical problem. Recall that regular expressions are called regular expressions because they can recognize regular languages. Well, regular expressions with back references, or regex wubber as they're sometimes called, totally break containment. They can now recognize an oddly shaped slice of non-regular languages too. Let's look at an example of that. Here's a regex that many programmers find themselves writing at some point in their career. It will recognize a string like this, but not a string like this. If you ever find yourself writing something like this, you're typically going to have a pretty horrible time in the very near future. There's a famous comedy Stack Overflow answer which doesn't answer very much, but it's very evocative of the experience you're likely to have. The problem with HTML tags is just like the problem with balanced brackets. If you have a nested structure where something needs to match up with something earlier in the string, it's not a regular language anymore, and in theory, regular expressions can't recognize them. This also means that finite automata can't recognize them. Our little extra backtracking rule we added to our graph is nice for us, but it's not really a valid finite automata rule, since it now has an extra bit of state in it. And all of this means we can no longer use the lockstep algorithm, essentially locking any algorithm that implements back references out of linear time complexity and into the exponential time complexity backtracking algorithm. But when developing Unix 7th edition in the late 70s, they either didn't know or didn't care about all of this. I guess it looked like a nice feature which would be relatively straightforward to implement, and so they did it. Then that gets released. The new features and sed start getting embedded into everyone's scripts. GNU Linux emerges and mostly copies the existing behavior of the standard Unix tools. And then Perl emerges and builds on this to make regexes a standard part of every modern programming language. All of it with back references and all of it with backtracking. And now there's no way back. Is this good? Well, you may have your own opinions on that. There's almost a technical version of the utilitarianism versus deontology argument in ethics. Probably the harm done by explosive backtracking occasionally is outweighed by the convenience that back references provide to programmers on a regular basis. But it does feel like a technically disappointing result that we'd have embedded this flawed approach as the default in so many places. I'd be curious to hear your perspective in the comments. I actually once showed the HTML Stack Overflow answer to my colleague who was for some reason talking about trying to parse HTML with regular expressions. Now, most of the time if you ever share that Stack Overflow answer, you feel pretty smug, and so he decided to take me down a few pegs. He informed me that our boss at the startup we were working at, his previous company was actually a web scraping business which made immense amounts of money, enough to start a VC firm and then to fund the startup we were all being paid by. And this web scraping business was essentially parsing HTML with regexes, the business. Everything was just regexes parsing HTML, extracting it, and then, I guess, selling that data. I don't quite know what they did. So it turns out the Chomsky hierarchy, it's more what we call guidelines than actual rules. But if you're interested in an implementation of regexes, which is based on the lockstep algorithm, one exists. It's called RE2 and it's written and maintained by Google, and it's used actually as the default regex engine for Golang. And I believe it was at least pioneered by Russ Cox. Aside from in Go, it's often deployed soon after an organization has become victim to a regex DOS attack and they want to use an algorithm that runs in linear time over its input. And of course, it does not support backreferences. And the link to that is on the ODE's website as usual. But backreferences can also be used to write some fun regexes, and there's kind of a famous example which was recently featured in a video that caught my eye. A couple of weeks ago, Matt Parker at the Stand Up Maths channel posted a video titled, and he did do this joke himself, but I'm going to do it again, "How on earth does caret dot question mark dollar pipe caret bracket dot dot plus question mark slash 1 plus dollar produce primes?" I hope it was as funny when I did it. He does a nice funny joke where the numbers emerge from a kind of portal under his desk and then chase him through the forest. So I'd highly recommend you go watch it. I'm going to put the link in the description. So go and watch that now if you haven't already seen it. Now, if you've watched these past 3 videos, I'm sorry, you're going to be unable to find this funny anymore. But you'll be unable to find it funny in the best possible way. One based on a critical, well-informed understanding of regexes. The most boring thing you will now know is that the regex that he's talking about is not a real regex. It's not a regular expression anymore. It's instead this ugly but kind of useful regex wb, or regex with backreferences. But so what? It still works, right? The second thing you may think is that regexes don't produce strings, they recognize them. But that's not actually true. Dedicated ODE's members who've done the exercise on this will know that you can also use regexes to produce strings just as well as you can use them to recognize them. So here's an example of the regex from Matt's video producing numbers. It's producing them in unary, essentially sequences of ones where the length is the value. I've tweaked it so that it refuses to generate strings longer than 30 so we don't get caught in an infinite loop or anything. I find the idea that regexes can recognize and produce strings very pleasing, because it mirrors the same thing from Chomsky grammars. Grammars describe a language, and a language is the set of all possible strings a grammar can produce. So you can use grammars to generate strings and to recognize them. This symmetry between generation and recognition is a very powerful idea. Sometimes, if you can't quite work out how to recognize something, if you can figure out a way to generate it, then this helps you solve the problem. And if you've ever done Stanford Code in Place, then their automated feedback tools actually leverage this in a genuinely fascinating way, which we may get to talk about in the future. All of this is to say, we can totally use this regex to generate strings, and this is true even if it does have backreferences in it. The third minor issue is that this regex actually matches or generates non-prime numbers, also known as composite numbers. Matt covers this in the video, and of course the answer is to
just write not. There you go. Not that. Piece of cake.
So, if we want to use this regex to produce prime numbers, all we need to do is write an evaluator for our finite automata which generates strings instead of recognizing them, supports backreferences, and instead of just a normal regex where we return success on the success conditions, we'll return failure on the success conditions and return success on the failure conditions. In layman's terms, we just shove the regex engine into full reverse. So, let's get coding. Except we can't. Because if I had a way to generate prime numbers in this way, I would need to be Turing Prize Award winner KLAC instead of the KLAC I really am. While it might feel intuitive that since we can negate the recognizing process to recognize strings not in a language, we should be able to negate the production process to produce strings not in a language as well, it doesn't work like that. This is more obvious when thinking about prime and composite numbers. It's very easy to generate composite numbers, just multiply some numbers together and there you go. But it's not at all easy to generate prime numbers, except by generating all the composite numbers and spotting the gaps. There are ways around this, of course. You could implement negative lookaheads, or you could just feed a list of strings of increasing length into the recognition algorithm. But in both cases, the regex is really then doing the work of recognition, not of production. So this regex will never directly produce prime numbers. If you can prove me wrong though, one of you will definitely make it into the next comments and corrections video. Which means Matt Parker posted a somewhat misleading title for his YouTube video. I know, this must come as a real shock and disappointment to you, but if he hadn't had that title, then you wouldn't get to see all those numbers come out of that portal and chase him through the forest. And it is called stand-up maths, not just maths, so really I think it's a pretty honest title. Let's have a look at some exercises. Okay. It's late now and I've just finished the exercises for you. The first one is 7 regexes and each one exhibits catastrophic backtracking given certain inputs. So your job is to find out what those inputs are. Well, there's an infinite number of them, but at least find one that takes probably longer than 5 seconds. They start off relatively simple and perhaps unlike the regexes you see every day, and then they move on to perhaps more realistic ones you might see in a horrible piece of code you're afraid to touch, and then perhaps to something a bit more unusual. The second exercise is to create a program which can identify regexes which are vulnerable to catastrophic backtracking or regex denial of service attacks, and then to generate candidate inputs for them that are likely to get them to exhibit this behavior. I'm actually kind of really excited about this one because there's loads of research out there which you can go and look at, and there's the possibility that someone watching this manages to contribute a fix or an improvement to an open source project or something like that. So that would be really cool if that happened. Do let me know if that's where you take it. And there's also a third members only exercise which represents my thanks and appreciation to the people who support me in making these videos. Loads members get ad-free viewing as well as extra exercises with every video. So if you're interested in signing up for that, of course I'll be very appreciative. It's $10, pounds or euros a month depending on where you are. And if you want to sign up for that, then go to the Odes website and various buttons and links will guide you on the way to finding out more. Finally, I've collected the resources I used to create this video, in particular Russ Cox's excellent series of technical essays about regexes. Every time I read those, I discover something new, just amazing technical writing. So I would highly recommend spending some time with those essays, particularly if you're interested in regex or systems programming or basically anything we cover on this channel. Those essays are really good if you like to read deep technical thinking, which really makes sense and probably makes you a better programmer through reading it. So yeah, highly recommend that. Also thanks to Matt Parker of Stand Up Maths for unknowingly contributing to this video. I have no affiliation with him at all, so he's not endorsed this video, but I enjoyed watching his, as I do many of his videos. So if you haven't watched his video already, I've linked it in the description so you can go and watch that one next. It's really nice and you get to see some numbers running around, which is always fun. The next video is going to set us up for a little festive recess. And when I say recess, I mean, of course, even more programming. Advent of Code starts on December 1st, as it does every year. Obviously, it's Advent, so same day every year. And for the past few years, I've been doing it and uploading my solves on YouTube. I'm not going to do that this year, but I am going to spend some time with this channel exploring the competitive programming and sort of puzzle solving scene. It's a very different kind of programming to normal programming, but I think we can learn something interesting from the people who do it really well and are kind of awe-inspiring, solve it in 2-minute types. Like the obvious question is, how do they do it beyond being pretty smart? And I think we can probably learn something, even if it's just how to have a bit more fun solving puzzles, which is always a nice thing to be able to do. And in addition to the more thought through produced videos on YouTube, I'm also going to be streaming my puzzle solves on Twitch. So if that sounds interesting to you, you can follow me over there and watch me probably stare at the screen for a long time on probably about day 13, 14. That's probably where it typically starts. Anyway, a lot more on that in the next video, which will come before December, so watch out for that one. That's it for this video. I will speak to you very soon and have a wonderful day.